We have already seen that any differentiation leads to an integration, meaning if f has derivative g, then g has antiderivative f. And we can start with the product rule. Which is, of course, this. And that becomes a certain integration. And at first, this doesn't seem too interesting. I mean, what do we expect to do? Have an integral and then realize that the integral has this pattern in it and use this in order to integrate it. It doesn't even seem like there's any compelling reason to make a rule out of it. But the idea actually becomes somewhat different when we split this integral into two. Or rather, the idea that will eventually emerge will look quite different. And what we do is we carry the second integral over to the other side. And we get this formula. And here, at first, one might think that this formula has a certain problem to it. The problem being that that c was removed. But then if you realize that any indefinite integral has an inherent c in it, then the c was just absorbed by the integral that was carried over to the right-hand side. So the formula is fine. What is the meaning of this formula? The meaning of this formula is that if you have the product of two functions and one of them can be acknowledged as the derivative of some other function, then you can apply this formula and come up with a different integral that you might hope it's simpler than the one you start up with. So I would like to start with an example, an example that will not can be done two ways, as we are going to see, because when you have the product of two functions, you can acknowledge either function, if that is practicable, as the derivative of some other function. So you have more than one choice. So in particular, I would like to begin with this integral and see how this formula would apply to it. Again, in order to apply this formula, you need to take one of the components and say, oh, you know what, this component is the derivative of such and such function, and then you can apply the formula. So I'm going to start with x and ask myself, is x the derivative of something I know? And the answer, of course, is x squared over 2. So I will take the derivative of, I will replace x by the derivative of x squared over 2. The two things are the same, right? And then I will apply this formula. And that will give me x squared over 2 times e to the x minus. And here I would have x squared over 2 times the derivative of e to the x. That's how the formula should be formally applied. And I get x squared over 2 times e to the x minus x squared over 2 e to the x dx. And this is the time where we need to evaluate this integral. And you know what, sometimes we might even want to do a little bit of cleanup. So for example, here you can take the 1/2 out and have x squared e to the x dx. But this doesn't change the nature of what you obtained, because the critical question at the end of the day is this integral any simpler than the one we start up with? And I hope you can see that the answer is no. I mean, it is by no means simpler than what we start up with. So it doesn't mean, so we apply directly this formula, which, by the way, we're going to call it integration by parts formula or partial integration. So this is called integration by parts or partial integration. And the reason is that you choose a part of the function that you have, in particular, a factor of the function that you have that you're trying to integrate, and you acknowledge it as a derivative of some other function. The moment you acknowledge it as the derivative of some other function, it's as if you find its integral, because you're saying, okay, so I have x here. The antiderivative of x is x squared over 2. So in some sense, I'm integrating x. So I'm integrating part of what I have. And that's why we call this partial integration or integration by parts. But if we look at everything that we did here, it was of no avail. And of course, you might think it's bizarre to start my examples of integration by parts with something that doesn't work. But I just wanted to show what happens in such situations, which is that it's largely a process of trial and error. You try different things. So here's what I'm going to try now. Okay, so now let's try to go the other way. What do I mean by that? So I have x e to the x, and I would like to focus on this and ask myself, is e to the x the derivative of something? And the answer is actually quite simple, right? E to the x is the derivative of itself. And here I want you to be careful about something. I mean, the way this has been written, it can be interpreted two ways. It can be interpreted as I just differentiated e to the x where it was sitting, which makes absolutely no sense. I can't just change something like that, or acknowledging that e to the x is the derivative of itself, and thus replace it accordingly, which is exactly what happened. So the other thing that I want you to realize here that should have been said in the beginning is that it doesn't matter which function comes first and which function comes second, and you shouldn't try to change the order of the function so that you apply this formula the way it appears here. You can always start with the second function or the function which is listed on the right as the function that is being acknowledged to be the derivative. The game that you're going to play with integrals is going to be the same. So what do? You skip the prime. Okay, so that's one way to put it. You skip the prime, and then you flip the prime over to the other component, like so. Then you need to carry out your differentiation and evaluate the situation. Do a little bit of cleanup, simplification, and then ask yourself, is this integral that we obtained here any simpler than the integral we start up with? And now the answer is sure it is. Sure it is. And we can finish this. We can say that this is just x e to the x minus minus e to the x plus c. And that's now, of course, one might ask, are we supposed to do this every time? No, the way these methods of integration work is that you usually need to acquire an experience after doing examples, and then little by little you get a sense about what is going to work and what is not going to work. And that's exactly what will happen here. So let's do another example. Another simple example. Actually, I would suggest that you pause the video and you try to do this example yourselves, x cosine x. And here comes the solution. What we're going to do here is acknowledge that cosine x is the derivative of sine x. And we're going to play the same game, which is what? First, suppress the differentiation, and then flip the differentiation in a new integral over to the other component. So x prime times sine x, and this will be x sine x minus the derivative of x, which is 1. Soon enough, I'm going to speed up a little here. That is, not have to write 1 times. I will just do it automatically, or I will even write this integral automatically with the derivative. But it's the first example, so we can use a little bit of a detail. So this is what we get here, and the antiderivative of sine is negative cosine. The two negatives give me a positive, and you get x sine x plus cosine x plus c. Okay, let's do something really cool now. So let's take the integral of ln of x. So what is an antiderivative for ln of x? Of course, the moment you say this, you might say, are you kidding? I mean, there are not two functions here, and the only function we see is ln of x. And if we knew what antiderivative it had, we wouldn't be doing this, right? But there's a very common trick here. Believe it or not, I'm going to assume the existence of the function 1 as a factor, and I'm going to also interpret 1 as the derivative of the function x. Okay, that's what I was saying a moment ago, that if you haven't seen such an example before, it's kind of hard to come up with this idea. But once you see it for the first time, it's something that you might want to consider in different situations. So what do we do here? Again, get rid of the prime at first, and then subtract an integral where you flip the prime. So here, allow me to go a little faster. So what is the derivative of ln of x? It's 1 over x. And you will get x ln x minus the integral of 1 dx, which gives you x ln x minus x plus c. It's actually, I think, quite useful for everyone to remember that this is an antiderivative for ln of x, x ln x minus x. Okay, let's go now with another example. So let's try the following. Let's try the integral of e to the x cosine x dx. Soon enough, you will realize that integration by parts is a wonderful method, a very compelling method that gives you possibilities that you wouldn't have imagined without. So this one is a very, very good example. So you look at that and you're like, okay, so how do I get started here? And the truth is, it doesn't really matter. You can take either e to the x to be the derivative of itself, or cosine x to be the derivative of sine x. And now, because of the previous example that we saw, one might say, can I take the function 1, which is in front, to be the derivative of x? Well, for the for the last one, I would say, don't get too excited about this. I mean, it's a nice possibility, but it's not like everything will be done using that. So actually, the two former possibilities are better. So take either e to the x as the derivative of itself, or cosine of x as the derivative of sine x. And, you know, like I told you, it can be done with both. Let me start by considering cosine x as the derivative of sine x. And what will that give me? It will give me, oops, not e to the x. It will give me e to the x sine x, right, minus. And now I need to take the prime and put it on e to the x. But when you take the prime and you put it on e to the x, the derivative of e to the x is e to the x. So allow me to, again, go a little faster here. Normally, I would have written derivative of e to the x, and then I would have acknowledged that it's equal to e to the x. But I think I can do it here. And there's nothing to clean up. You can look at it and ask yourselves, is what we got here simpler than what we started up with? This is usually the question that you need to ask in integration by parts. And the answer is no, not necessarily. I mean, I don't see why the integral of e to the x sine x is simpler or easier to work with the integral of e to the x cosine x. And that's why I said that what I'm showing to you here is just a new possibility that is being added to how we do things. So instead of giving up and say, well, that seems to be a dead end, what we're going to do is, believe it or not, apply one more integration by parts. It's like you do something. Isn't that one of the strange things to do? I mean, to have done something that didn't seem to work and then do it again. Well, in this case, you will see what will happen. So, and again, I'm not saying that this is something that will happen all the time. But what I'm going to do here is try to force one more integration by parts by acknowledging the fact that sine x is the derivative of what? Can you answer this? Sine x is the derivative of what? I hope you all answered negative cosine x. That's what it is. So I'm acknowledging sine x of being the derivative of negative cosine x. And now I can carry out my integration by parts. Now, please be careful. Here, exactly because you have a minus in front and integration by parts involves more than one terms, it is wise to open a parenthesis and carry out the integration by parts inside that parenthesis. So you will have e to the x times negative cosine x. And then you're supposed to take the prime and put it over to e to the x. But as we said already, the derivative of e to the x is e to the x, so allow me to write e to the x negative cosine x, knowing that I have already carried out my integration. And this will give us, now we need to do a little bit of cleanup. So e to the x sine x minus, you have two minuses here, right? Minus in front of the parenthesis, minus on the cosine, so that will give you e to the x cosine x. And then you have three minuses, right? In the parenthesis in front of the integral and inside the cosine, so that will give you minus e to the x cosine x. We did our cleanup, and now things are bizarre. I mean, we came up with the same integral that we started up with. And at this point, many people would give up, say that, it seems that this is just a vicious circle and we're not going anywhere with it. But then, if you look at it carefully, and let me rewrite it with just the very first part of this string of equality, so e to the x cosine x dx equals to e to the x sine x plus e to the x cosine x minus e to the x cosine x dx. If you look at it as having a relation between something that you don't know and things that you do know, so you certainly don't know what e to the x cosine x is, and you have it twice, but then you connect it with things you know. I mean, it's pretty much like saying I have a number x that I don't know, and it's equal to 4 minus x. What do you say in such a case? You say, I give up here? No, you don't say I give up. You just bring all the unknowns to the left-hand side, and you say 2x is equal to 4, and eventually you find that x is equal to 2. Believe it or not, that's precisely what we're going to do here. So what we're going to do here is, again, we're going to work now with this equality. We're going to bring e to the x cosine x to the left-hand side. So we're going to get two of them. And this is going to be equal to e to the x sine x plus e to the x cosine x. Now, to keep things balanced, we do need to put a plus c. And eventually, we divide by 2, both sides by 2. And this gives us 1/2 e to the x sine x plus e to the x cosine x plus c. Please notice that normally you would have written c over 2, but c over 2 is as generic as c. So yeah, it seems that I'm committing a very elementary mathematical error here, but the truth is that there's no such error. It's just the fact that if you take a generic constant and you multiply it by any non-zero number, you pretty much get another generic constant, and you shouldn't have to denote it in any different way. So and you will see that happening with integration again and again. It's not something that you will not see after this example. So we can actually look at what we just did and realize that the method of integration by parts in general is something that has to be learned one example at a time. And once you look at an example, you have to try to look at the interesting features of the specific example, and so that next time you come across something similar, you'll be able to do it. I would like to do one more here. So let's try something like x squared ln x dx. This should be treated in a similar way like ln x, and I'm just saying this. Pause the video, try to see if you can get it to, if you can solve it, and then we're going to do it together. So here's what we do. We acknowledge that x squared is the derivative of x cubed over 3, sorry, times ln x dx, and this will be x cubed over 3 ln x minus, and now you carry the derivative over to the other function. And what is the derivative of ln x? It's 1 over x. And now the moment you see this, you understand that things are nice for us here. We have 1/3 integral of x squared dx, and the integral of x squared dx is x to the third over 3. So this will give us x to the third over 3 times ln x minus x cubed over 9 plus c. And that's this integral. I would also like to say that in this presentation of integration by parts, we avoided to use an approach which is quite common at college settings, which is to think of this formula. Sometimes people write it this way. So uv prime is equal to uv minus u prime v, or the other way around. So for example, when you have something like x e to the x dx, people will say, oh, okay, so my v prime is e to the x and my u is x, so I need to find v. So v is going to be also e to the x, u prime is going to be 1, and then you're applying the formula. You say that this is u times v, which is x e to the x minus 1 times e to the x. The reason I didn't do it this way is because once you look at the formula of integration by parts, it has an inner harmony, an inner beauty that doesn't need to this additional notation u and v, which is really not used further than college courses. So that's why I avoided to use this in the formalism that was introduced, and that's the way that I'm going to proceed. There's nothing wrong using this formalism if somebody feels comfortable with it, but as you can see from the examples that we saw above, it's totally avoidable. You just acknowledge your component, which is a derivative of something, then you first suppress the derivative, and then you flip it over to the other side in a new integral that you subtract. So there's nothing here to really compel us to use this method. And that's our first introduction to integration by parts. We're going to do a few more examples in a later video. Thanks for watching.